Hello everyone, welcome back to my YouTube channel. So, this video is on operational amplifiers. In this series of video lecture, we'll be discussing about operational amplifier applications. So this part is 3.3, and in this part, we'll be discussing about inverting summing amplifier. Okay, amplifier as a summer or summing amplifier we'll discuss. So in that first one is inverting summing amplifier. Let us go into the details of that. So before going to details of inverting summing amplifier, now first let us understand what makes amplifier to add two signals to some many input signals. It is because of its characteristics, that is its input impedance is extremely large in terms of it is infinity, we say. So when the input impedance is large, we can give more than one input signal. So no matter how many inputs you give, all the inputs will be added together, and amplified version of that added signal will be available at the output side of the op amp. So such circuit is called as summing amplifier, or sometimes it is also called as adder circuit. Depending on the sign of the output, the summer circuits are classified as inverting summing amplifier and non-inverting summing amplifier. The meaning is if we give input signals to inverting summing amplifier, then output will be having a negative sign or the phase inversion will be observed. We give it to non-inverting terminal, phase inversion will not be observed. So depending on this, there are two types of summing amplifiers. So first let us discuss the inverting summing amplifier. Now, so this is the circuit diagram of inverting summing amplifier, in which we have a pump and we have connected two inputs V1 and V2 to the point A, and this point A is in turn connected to inverting input terminal of a op-amp. Fine. Now, so in the input side we have two inputs and two resistors we are making use, R1 and R2, and I1 and I2 are the current flowing in the branches R1 and R2 respectively. Fine. Now, here also we make use of a virtual ground concept. What the input terminals of op amp will be always at the same potential. So what is the meaning of that is, if a non-inverting terminal is connected to ground, if point B is connected to ground, its potential will be zero. Now what we can say from the virtual ground concept is VA, potential at A, is equal to potential at B, which is equal to zero. Okay. Now from the input side, let us try to write the equation for current. Fine. So in the first branch, the current flowing is I1. If you want to have a current, this expression for this current I1, then we'll get it as uh, voltage at this point minus voltage at this point divided by the resistance through which the current is flowing. So what you can write is I1 is equal to V1 minus VA divided by R1. So from the virtual ground concept, we have VA is equal to 0. If I make VA 0, so I1 is equal to V1 by R1 will be having. Okay, let us call this as equation 17.1. Similarly, for the branch R2 also, I2 current I2 is given by V2 minus VA divided by R2. Since VA is 0, so we'll be remaining with V2 by R2. Let us call this as equation 17.2. Now let us apply KCL at node A. Okay, let us apply KCL, Kirchhoff's current law at node A. What it says is incoming currents is equal to sum of incoming currents is equal to outgoing current. So outgoing current is I here, incoming current is I1 and I2. So I1 plus I2 is equal to I. Now, so uh, let us call this as equation 17.3. Now we know that input impedance of amp is infinity or very large. None of the current will enter into the op amp. So meaning is whatever current comes in at point A, it has to reach the output side by passing through the resistance RF, that is feedback path. So in the output side also, let us try to write the expression for I. So how we'll write is VA minus V naught divided by RF. That is VA minus V naught divided by A 0, so you make it 0, it will be minus of V naught divided by RF. Let us call this as equation 17.4. Now we have the expression for I. expression for I1, expression for I2. Let us substitute all these three parameters into this expression, that is 17.3. So that is what we had done over here. This is I is equal to I1 plus I2 written in terms of voltage and currents. Now, let us solve it further. So this RF, which is there in the LHS denominator, let us send it to the RHS part and multiply it with each of the term. Will be remaining with minus. You keep it outside. Along with the minus sign, you have to send RF to the RHS. So RF by R1 into V1 plus RF by R2 into V2. Let us try to simplify it further. Let us make an assumption that value of R1 is equal to value of R2 and it is equal to R. So then what happens is we can take R1 and R2 common. So and RF is also common. So RF divided by R will be the total common out. In the bracket will be remaining with V1 plus V2. Now thus the circuit amplifies the addition of the two input signal and acts as a summing amplifier. What he's saying is in this bracket V1 plus V2. What are these V1 and V2? V1 is the input signal 1, V2 is the input signal 2, and this is the expression for output signal V0. So output signal V0 will be the added version of the two input signal. That is what he is trying to say. Let us take one more assumption. If R1 is equal to R2 is equal to R, we have made this assumption for simplicity. So then what happens is this RF by R will vanish. So the remaining V0 is equal to minus of V1 plus V2. That's output voltage is equal to sum of two input voltages. What is this negative sign is indicating is whatever output we are getting, it is the inverted version of the inputs applied to the inverting terminal. This completes this part of application, that is inverting summing amplifier. Thank you.